So, metric spaces, countable sets, this is basically the world in which we're going to be working, right? Metric spaces, this is, really is a course of, about metric spaces, analysis on metric spaces, or the basics of it. Okay. So, and before we get there, we're sort of doing these maybe simpler things called countable sets. So, okay. Okay, so, yeah, so first we're just going to finish up countable and uncountable sets. So countable and uncountable sets, and then we'll go into metric spaces. Okay. So the first thing we're going to show is the following theorem that if you have a sequence, so you have a set of sets, right? You've got E sub n, E1 through infinity, which is a sequence of countable sets. And then the claim is that then the union, if you take the union of all these sets, then this is also countable. Okay, so a countable union, in English, a countable union of countable sets is still countable. Okay. Okay. So, does anybody know how to prove this? Anybody remember? Presumably you've read it. Anybody have an idea of how you do it?
Is this the infinite array?
Yeah. This is the one where you say, well, look, being countable, right, means that each one can be expressed as a list, right, as a sequence, right. So express each E sub n as xn1, xn2, xn3, right, as a sequence, right? So E sub 1 would be x11, x12, x13, et cetera, E12 would be x21, x22, x23, et cetera, right? So these are the elements of the nth set for 4 and being 1, 2, 3, et cetera. Right, and then you make this array, right? You say, consider the array x11. So first you take E1, and then you take E2, and then you take E3, right? And you place them all in this big list here, and then you create a new list where this one is the first. This was your first element. This is your second element. This is your third element, right? And then you loop around like this. This is your fourth, fifth, sixth, right? So you put them in one long list, right? You take all of these lists and you make them into one long list that covers every single element, right? So you create a new list. I don't know if I called it anything. Yeah, it's create a new list. Let's call it E1, E2, E3, etc. That hits that. It's every element in the union. That it's every element in the union, right? So then what you have, so there might be some duplicate elements, right? So maybe this element and this element are the same, right? So this is this map. This gives you a map, right? Yields a map. Little e, going from n into the union, right? But it might be, it might not be one-to-one, right? It might have too many, it might, you know, it might hit elements more than one time, okay? So, but what you can do is, but you know, each element here is associated with a number here, right? Perhaps more than one, right? Perhaps more than one, but every element here is associated with a number here. And so what that gives you is gives a map from E sub n into this, which so it goes into n. Okay. So what we have is a correspondence between this and a subset of n, right? We have a one-to-one correspondence between this and this set, right? So, right, and so so we know that this this can be placed with a correspondence with a subset of a countable set, right? Since this thing is definitely infinite, right? So we can make this we can make a correspondence between this and a subset of n, which means that this guy is either finite or it's countable, right? We know it's not finite, right? We know it's not finite because we just look at the first row. The first row is infinite, right? Certainly, E1 is not finite. Right? It was countable, right? So it must be countable, right? Does it make sense? Being a subset of n means that it was either finite or countable, right? We know it's not finite, so it must be countable. Okay. Okay, so that's nice. Countable subset. Countable union of countable sets is still countable. Good. Okay. Okay. The next thing we're going to show is that if you take tuples, so if you have a countable set, so A countable, and then B collection of n tuples, so A1, A2, to AN, where each of the ANs, each of the AIs is in A. So this is the Cartesian product, basically. Do you guys know this term, Cartesian product, right? Like if you have R, you have like R cross R, right? You have a Cartesian product. So this is you can think of this as AN, just like we think of Rn. It's just vectors of elements in A, right? So this is what's called the Cartesian product. So this is AN, the Cartesian product of the of n copies of A. Okay. So if you have a countable set, and then you look at the Cartesian product of countable of these sets, then B is still countable. Okay. So again, in English, a Cartesian product of countable sets is still countable. Yeah, and really we don't have to have, this doesn't have to be the same Cartesian set. It could be different ones. Like, it doesn't have to be the same, it doesn't have to be the Cartesian product of the same set. You could have a countable, you could have one countable set against another countable set, et cetera, right? You could have A1 cross A2 cross AN, where each of these are different countable sets. But as long as they're countable, this is gonna be, the product is still gonna be countable. Okay. Okay. Anybody know how to do this? Anybody remember how to do this? This one uses the previous theorem, actually. So the way you want to think about it is you consider, so pick some, let's say, so A is countable, means that A can be written as a sequence, right? Right, we can express A as a sequence, right? So now consider the Cartesian product of just A1 cross A. Okay, A1 cross A. So that is, we're just looking at pairs where A1, A, and the second one is, anything. Okay, so you've got this first element, and then you've got a fixed first element, and the second element ranges over all of A. Okay. Okay. Right. Is this countable? Sure. Right. Because the second element is just ranging over A. Right. So all we've done is we can make a map from here to A just by projecting onto the second element. Right. And that would give us a one-to-one correspondence between this guy and A. Is that okay? You guys getting it? Okay, right, so it's, right, this is basically just a copy of A with an A1 stuck on it, right? So this is clear, right, it's countable. It's countable, right? Okay, but then now consider the union of all these things. Union, so now now take A2 of that, A3 of that, replace this by A2, replace this by A3, replace this by A4, et cetera, right? And let's take the union of all those things, right? If we take the union as I goes from 1 to infinity, right, is that countable? Sure, why?
By the last theorem.
By the last theorem, right? It's a countable union of countable sets, right? Each of these sets is countable. We've got a countable union of countable sets, so it is also countable, right? And you see what that is, right? That is just A cross A, right? That is, we're allowing the first thing to be anything in A, and we're allowing the second thing to be anything in A. That's the same thing as A cross A, right? That's right. This is the same thing. This thing above is the same thing as just A1, A2, where A1 and A2 are in A, right? Namely, A cross A. Right? And so, so what we see is that if we take the first, if we take, A cross A, if you take A, then A cross A is countable, right? And you can see that we can just do it by induction. You can get all the way up to the nth product, right? So that's it. You just keep on going until you hit the end by induction. Is that okay? I can't tell if you guys are feeling all right or not. Are you feeling okay? Okay. Okay. Thank you. You have to make your expressions more exaggerated for me, because I can't read expressions. Okay. Okay. So in any case, this is nice. So far we've gotten that countable union of countable sets is countable. A finite Cartesian product of countable sets still countable. Okay. But, oh, yeah, so corollary is that the rational numbers are countable. Right? Because what you can do with the rational numbers, anybody see how we would get this? Like, what does this have to do? Anybody see a relation between this and the last statement about Cartesian products? Can you take Q and then make it look like a Cartesian product of countable sets? What's Q? Q is, remember, things of the form P over Q, where P and Q are rational, are integers, and Q is non-zero, right? So what we can do, anybody see what we should do here?
Well, P and Q, or
Yes.
P and 1 over Q, I guess, are both countable, so
Yes.
somehow, like.
Yeah,
come together.
great. So that's the idea. So what you would do is you would given, you create a map from Q to Z cross Z. You create a map from Q to Z cross Z. And the map would be, take your rational guy and then express it in lowest terms. Right, express it in lowest terms. So it'll become P over Q. Right. The reason I want to do that is that there are infinitely many ways we can express each guy, right? So like, 2/3 could also be 4/6 and so on and so forth, right? There's infinitely many ways. I don't want to deal with infinitely many expressions, right? Like, which P over Q do I choose? Put it in lowest terms, right? Put it in lowest terms. Assume that if it's negative, assume that the top one is the negative one, so that we have a well-defined way of doing this. Right? And then map that to P comma Q. Right? Okay. So right. So that gives us a one-to-one map. That gives us a one-to-one map from Q into Z cross Z. Right? So what does that give you? That gives us that Q is one-to-one equivalent to a subset of Z cross Z, which is countable. Right? In other words, Q sits inside of a countable set. Right? Q is equivalent to something that sits inside of a countable set. Again, Q is infinite, so it must be, sitting inside means it's either finite or countable. Since it's infinite, it is countable, right? So Q is countable. Okay. Another way you could see that, maybe a more sort of hands-on way you could see that, is just by, you could say, consider the interval 0, 1, and we're going to make a list of all the rational numbers in here, right? We'll say, look at 0, 1, then we'll move on to things with a denominator of 2, right? We don't need 0 over 2 or 2 over 2, those are already in there. We look at things with denominators of 3. We look at things with denominators of 4 that haven't been counted already. We look at things with denominator of 5, et cetera, right? And in doing this, we get every single rational number between 0 and 1, right? Which means that the rational numbers between 0 and 1 are countable, but then you can do it for every interval, and that's a countable union. That'll be a countable union of countable sets, right? And so Q is again countable. Maybe that way is more straightforward. Okay. So alternate viewpoint. Observe that the rational numbers between 0 and 1 is countable. Right? And then just take the union over all intervals, over a countable set of intervals. So yeah, so but I think in the line of this story that we're telling right now, the best way to think about this is that, oh look, this is the subset of a Cartesian product, and Cartesian products of rational Cartesian products of countable sets are still countable. Okay. Okay. Okay, but what we're going to see right now is the following. If we look at the set Z mod 2Z, that is 0, 1, okay, just zeros and ones, okay, and we take if we took like a finite Cartesian products of this, well, that's still going to be countable, right? Because this is countable, right? And we're taking a finite Cartesian product. That's fine. That would still be countable. But what if we take an infinite Cartesian product? And the answer is that it actually turns out to be uncountable now. Okay, so that is this theorem that we're going to do next, which is that the real numbers are uncountable. Or maybe I should, let me not say it that way. The set of all sequences of zeros and ones is uncountable. So that's what I mean. That's what I mean by this thing, right? That you take, infinitely many A1, A2, A3, blah blah blah. It's an infinite sequence now where each of the guys is in 0 or 1. Okay. So what we're saying, here is the theorem is that this thing is uncountable. Okay. Yes.
You said Z mod 2 is countable?
Yeah, because I'm sorry. It's finite.
Okay.
Yeah. Sorry. Yeah, it's at most countable. Yeah. Yeah, and I get. Yeah, I'm being very sloppy here. So this thing to the 10th power is not countable, but at most countable. It's finite. Yeah, sorry, careless. Okay. Okay, so this thing, the proof of this uses the famous Cantor's diagonal argument. Cantor's diagonal argument. Does anybody know that offhand? Cantor's diagonal argument, like how you use Cantor's diagonal. Okay, so here's how it goes. You say, well, we're going to do by contradiction. Suppose, let's call this set E. Suppose E is countable. Suppose E is countable. Then it's expressible as a set E1, E2, E3, etc., etc. Right? So suppose that there's only a countable number of sequences of zeros and ones. Okay? Okay. So then write each one down. So consider each one, each sequence. So E1 is going to look like E11, E12, E13, E14, E15, etc., etc. Where each of these things is a 0 or a 1, right? It's a sequence of zeros and ones. So here's the first one, E2, E21, E22, E23, E24, E25, etc. E3 is going to be E31, 31, E32, E33, E34, E35, etc., and so on and so forth. Okay? So you write everything down. And then you create a new sequence. So now create a new sequence, E star. Okay. And E star is going to be, let me define an operation, twiddle. Okay. So twiddle, what twiddle does is, if you say twiddle over 0, it's 1. Twiddle over 1 is 0. Okay. So it just flips them. Okay. So if I say E11, if E11 were 1, this E11 twiddle would be 0. Okay. Okay. Or maybe I should call it star. Yeah, I'll call it star. No, I'm going to call this twiddle. No, I just call it star. Sorry. Okay. In any case, okay. So you create a new sequence, and the sequence is going to be you take the diagonals. Okay. You take the diagonal elements, and then you toggle each one of them. Okay. So E11 twiddle, E22 twiddle, E33 twiddle, and so on and so forth. Okay. So you go down the diagonal, you take that sequence of elements, and then you flip each one. Okay. 1 becomes 0, 0 becomes 1. Okay. And then you notice, right? So what you notice is that so is E star the same thing as the first sequence? Could E star be the first sequence? No, why not? Yes?
E11 and E11 twiddle are not the same.
That's right. This and this, right? The first element of the sequence are not the same, right? Could this equal to E2? No, same reason, right? The second element of this disagrees with the second element of this, right? Can't be E3 because the third element of this disagrees with the third element of this, right? So, so you notice that for each I, the ith element of E sub I disagrees with the ith element of E star, right? I going from 1 to infinity, right? And so E star cannot be any EI, right? E star is not equal to any of the EIs, right? E star is not on the list, okay? But E was supposed to be all the sequences, right? Right? E star can't be on the list, so E star is not one of these guys. That means E star is not in E, right? So E star is not in E, right? Right, because we said E was countable, and here's the list of all the elements in E. But E star is not any of those guys. So E star is not in E, but that's a contradiction. E star is in E. It's a sequence of zeros and ones, right? It is a sequence of zeros and ones, and so that we have a contradiction. E could not have been countable, right? But E is in E, so contradiction. So E is uncountable. Charlotte, yes?
Why are we using the twiddle? Like, that just seems kind of random to just place that in for E star. Like, what's the reason behind that?
I just needed a notation. If you want, if you want, I can make it a function. Like I could say, let's create a function phi where phi of 0 is 1 and phi of 1 is 0.
So it's just a way to turn E star into like a binary function, basically, or a binary set of just zeros and ones.
Well, I mean, here's what I want to do, right? I want to, the idea is to create, first you put all of the you take all of the sequences, you put them into a list, right? And then you make a new sequence. The new sequence is obtained by going down the diagonal, and then if this is creating something that disagrees with that element, right? So if this is a 1, I want my new sequence to be 0 there. If this is a 0, I want this to be a 1. If this were a 1, I want this to be a 0, and so on and so forth. Right? So I'm just creating a way that I can write that down easily.
Got it. So like hypothetically, you could have picked like 3 and 4 as the 0 and 1s, and it would still disagree.
If I were talking about a sequence of 3s and 4s.
Yeah. Okay.
Yeah. So for example, if we were talking about the real numbers, say, and we said the set of sequences of 0, 1, 2, 3, 4 through 9 is uncountable. Right. So you can do the same sort of argument for like decimal representation. So like let's look at all the numbers between 0 and in the unit interval 0, 1. Right. Everyone in there is expressible as a decimal, right? x1, x2, x3, something like that. Everybody in there has a decimal expression, right? So to show that that's uncountable, you'd say, well, suppose it is countable, right? We can do exactly the same thing. You say, suppose it's countable, then make a list of them, right? There'll be some first number, there'll be some second number, some third number, and so on and so forth, right? And supposedly that list contains all the numbers between 0 and 1, right? But I'm going to create a number that isn't on the list. And the way that I'm going to do it is I'm going to look down the diagonal, and then whatever the number is here, I'm going to choose something that's different from it. If this is a 1, I can choose anything as long as it's not a 1, right? If this is a 2, I can choose anything, whatever this is, I can choose, anything from here as long as it disagrees with this. Okay. And then you see that by doing that, I would create a number that is not on the list, right? Because it would disagree with this number in the first, in the tenths. It would disagree with this number in the hundredths place, and so on and so forth, right? So, so that would create the contradiction, because supposedly this was listable, and I had a list of all the numbers, but I've just created a number that disagrees with every single one of them. Okay, that's exactly what we're doing here. This is sort of a simpler version because we're doing only 0s and 1s, so we can just flip it. If it's a 0, change it to a 1. Here, we have to say, whatever number it is, choose, maybe choose to make it systematic, choose the lowest number that disagrees with it. Okay, so in any case, this is Cantor's diagonal argument. Cantor is the mathematician who basically created this whole area of like countable sets and thinking about infinities and stuff like that. Yeah, he was actually sort of reviled. Is this the right way to say reviled by other mathematicians of the time who hated his work, and he actually eventually had a mental breakdown because of that, because of all the scorn he got. But many years later, great mathematicians really had said, nothing shall shake us from the paradise that Cantor has created. And they really appreciated his work. So, what's the moral? The moral is don't care too much about what other people think. Okay, yes.
I just want to make sure I understand like the implications of this correctly.
Yes, yes.
Is it because like this set E is like a subset of the real numbers, and because E is uncountable,
Yes.
that makes the real numbers uncountable?
Yes,
Okay.
yes, yes. So what we just showed here is that 0, 1 is uncountable,
Mhm.
right? The interval 0, 1 is uncountable, and, you know, it's a subset of R. And so, you know, R can't be countable because if you're a subset, one of the thing we proved last time is that any subset of a countable set is either finite or countable, right? So this is a subset and it's uncountable. So the ambient space could not have been countable. Kind of a cuter way of thinking about it is that, you know, these sequences of zeros and ones you can think of as binary representations of the 0, 1, of 0, 1, right? You think of this as a binary sequence, right? Right, where this is like not how many tenths you've got, but how many halves, right? This is how many quarters, how many eighths, and so on and so forth, right? So this is actually you know, binary representation of the numbers between 0 and 1, right? Rather than using the clunky decimal representation. Okay. And so what you see, we didn't have to do this actually. We didn't have to do this stuff on the left. Right? This stuff on the right says 0, 1 is uncountable. And so R is uncountable. Okay. 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 Everyone all right? Yes, yes. Okay, good. Okay, so now we're going to, now we get into metric spaces. Okay, so a metric space is just a space that has a metric. Okay, and a metric means like a way of measuring distance. Okay, but you know, what do we mean by distance? It has to satisfy certain properties. Okay, so here we go. Let's you know, make this formal. So you have a set, and you have again a function, a real value function d on the Cartesian product. So it takes in two elements and returns a number, right? This is, you know, a distance, right? This is going to be our distance. It takes in two things and then returns the distance between them. Okay, so it has you know, this function. So if for all p and q in x, we have the following three properties. Then we say D is a metric, and x comma D is a metric space. Okay. So the three properties are kind of, you know, what you expect. One is that the distance from P to Q is the same thing as the distance from Q to P, right? You know, that should be true. Another is that the distance from P to P, the distance from P to Q should be positive unless P equals Q, in which case it should be 0. Okay, so distance is always positive unless you're talking about the distance between you and yourself. Okay, and then the third thing is that distance from P to Q should be controlled by the distance from P to R plus the distance from R to Q. Okay, so I should say for any P, Q, and R in X. Okay, so the distance from me to Anne should be controlled by the distance from me to Charlotte plus the distance from Charlotte to Anne, right? In other words, the triangle inequality, right? The distance from me to you is controlled the distance from me to some intermediary point, and then the distance from the intermediary point to that third thing. right? So triangle inequality. So those are the things that turn out to be, these are what we want a distance to satisfy. Okay. And of course, you know, the most straightforward examples are the real numbers, where the distance between 2 points is defined as the absolute value of the difference, right? So that's kind of the standard one, right? You have you have numbers, and you have distance between numbers being the absolute value of the difference, right? Rk, where the distance between two vectors is the magnitude of the difference of the vectors, right? And those are sort of your standard metric spaces. One kind of odd one is to take any set. So you can take any set, E any set, and define D xy as 1 if x is not equal to y, and 0 if x equals y. Okay, so I can make this classroom into a metric space. You know, the people in this classroom are a metric space if you put this metric on it. And the metric is, you know, if I differ from the other person, then the distance is 1, right? But if I'm talking about the distance to myself, the distance is 0. Okay, right? The triangle inequality still holds, because if I think about the distance from me to Jackson, say, that's 1, and that's certainly less than the distance of me to somebody plus the distance from that somebody to Jackson, because, you know, if that somebody is me, it's 0 plus 1, which is 1. If it's somebody, it's not me, then it's, you know, 1 plus 1, which is 2, which is certainly greater than 1. Right? So you can. This is called the discrete metric. Okay. It's another example. Okay. So these are kind of the standard examples of metric spaces. Another kind of standard example is to take Rk and put on what's called the taxicab metric. Okay, so the taxicab metric goes like this. If you have x, y, then the distance is the sum of these lengths. Okay, you would take this distance and add on this distance. Okay, so if let's say that this point, let's call these things x1, y1, and this one x2, y2. Then what you would add on, you would take the distance between those 2 points would be absolute value of x1 minus x2 plus absolute value of y1 minus y2. Right. In other words, these perpendicular distances. Question? No. Okay. Right. So it's a taxicab metric because you imagine that you live in a taxi. You're living on a grid, right? You can't go through the buildings and stuff. You have to go on the streets. The streets are all perpendicular. The streets are all laid out on a grid. Okay. So that. It's easy to check. That is also a metric. Okay. So some standard definitions for Rk. You all, I don't think I need to define these things. Open sets, open intervals. I'm sorry, R for R. Open intervals, closed intervals, etc. If you guys know what those are. In Rk, we have something called a K-cell. K-cell is basically just a product of open intervals. So you take A1, B1 cross A2, B2 cross AN, AK, AK. Right. So, right. So you know, in R2, you would take some interval A1, B1, and cross it against some interval A2, B2, right? And that would give you this rectangle, but not the boundary, right? So you wouldn't have the left edge or the right edge or the bottom or the top edge, right? Right. In R3, you see that you'd get a cube, but not including the skin of the cube. Okay, and so on and so forth. So K cells, that will be a useful term. These are sorts of like generalization of intervals. So in R, you know what intervals are. In RK, you don't really have an interval, but we have these things called K cells as a generalization of an interval. Okay. Another way of generalizing, and this is the more useful one, is with balls. So for x in RK and r greater than 0, right? We define the ball of radius r centered at x is defined as, you know, all the points, you know, let's call this, it's all the vectors y in Rk such that the distance of x from y is smaller than r. It's just a sphere. Right? You've seen this before. Right, you have some point x in Rn, right? And then you look at everything whose distance is smaller than r, right? It's just a sphere. Okay. So this is what we call a ball. An open ball centered at x with radius r. Okay. And if I include the boundary, then it's a closed ball. Okay. So this would be a closed ball. Okay. Okay. So those are sort of, you know, ideas in this Euclidean space, right? Which is one of the examples of a metric space. But in the general metric space, so we're going to take those ideas and then generalize them to metric spaces, right? So instead of you know, it won't be exactly the same thing. Hold on.
No, 119 has a laser too.
Sorry, we're having a class right now? Oh, it's Tom. Okay, so let's say that xd is a metric space. The first thing we do is define something called a neighborhood. And this is basically the same thing as a ball. Okay. So if I write n sub r, so let's say that x is a point in x, and r is some real number, some positive real number, then when I write n sub r x, what that means is all the points in x whose distance from x is smaller than r. Okay, so this is called a neighborhood. Right? Neighborhood centered at x of radius r. Okay. One thing that the book doesn't define, but I find it is really handy, is the following notation. So we're going to say this, where this is the same thing as the neighborhood, but you exclude x itself. Okay, so it's, you know, if you think about it in the Euclidean setting, it's the ball, but excluding the center. Okay, ball excluding center. I call this the punctured neighborhood. Okay. Okay. The next definition, sorry, I'll just finish with this one. Suppose you have a set, let E be a subset of X, and P be a point of X. If every punctured neighborhood of P intersects E, we call P a limit point of E. If every punctured neighborhood of P intersects E, we call P a limit point of E. Okay, so like if I'm in R, suppose I have something like this, just the open disk in R2, right? I take something on the boundary here. I take a point P here, and then you notice that no matter what neighborhood I take, I always intersect E, right? No matter what punctured neighborhood I take, I always intersect E, right? No matter, you know, it keeps on intersecting E, keeps on intersecting E, right? So that means that this guy is a limit point. Okay, this guy here, well, maybe some punctured neighborhoods intersect, but not all of them, right? I can find a punctured neighborhood that doesn't intersect E, right? Right. Point in on the inside here definitely, you know, is a limit point, right? Okay, we'll do more of this next time. Sorry, that's all. We'll stop here for today. Yeah. So yeah, there's going to be a whole lot of definitions from here on in. For amusement, I suggest searching on YouTube for the parody Hitler Learns Poinsett Topology, where they've taken this old war movie where it's this old German war movie where like things are going bad for Hitler and he gets really angry at all his subordinates. But they've, you know, instead of, and then they've subtitled it with him, and he's talking to a bunch of topologists about topological definitions. It's like, you know, what is this limit point? You know, and why do you have to make things so complicated? And everybody's like, oh no. And anyway, it's pretty funny. Yeah. Okay, that's it for today.